So let's jump right into it. I think this audience knows what DARPA is, but that's always a great place to start because you can never be sure.
There'll be a test later. It's great to be here with everybody. I think many people in this community know DARPA, the Defense Advanced Research Projects Agency. We are the slice of science and technology in the Defense Department with the mission of making the pivotal early investments in breakthrough technologies for national security. It's a mission that dates all the way back to Sputnik, and the fact that realization at that moment of national shock and surprise that you needed a place whose day job was to come in every day to prevent that kind of surprise. And like all of our leaders across 60 years of history at DARPA today, we think about how preventing surprise not as being a defensive activity, but the best way to do that, we think, is to go out and create technological surprise. And so that mission is exactly the same across all these years.
So we have a new administration. You are, as I understand it, the one political appointee at DARPA.
That's right.
So what do you anticipate changing?
Well, obviously when the administration changes, lots of things are going to change. DARPA is a place that's actually about change, and other than our mission and our culture, which we work very hard to continue to reinforce, and that I think have been strong and vibrant across a lot of many different eras. I think whatever happens with any new administration, you should expect changes at DARPA, because we know geopolitics will continue to change, we know technology will continue to change, and so I think the agency is cranking on what it's cranking on, and absolutely will continue to evolve in the face of whatever comes next.
So let's talk about what you're working on at DARPA now. So I know everybody, it's 2 p.m., but this is the time when you should wake up, because we're going to talk about some exciting things like killer robots, brain interfaces, and space planes. So let's start.
We're doing 2 of those 3. We're not doing the first, just to be clear.
Right. Let's talk about, let's start with space.
Great.
I don't think DARPA gets associated with, you guys don't get the credit. What are you doing with space?
We're, as in many things, we play a small role, but I think it can be one that's really critical for shifting trajectories. So, if you think about what's happening in space today from a national security lens, number one, it's a domain on which we are critically dependent. There's nothing that we need from either an intelligence perspective or a military perspective that we can do effectively without space. Something as simple as navigation is completely dependent today on GPS almost in every part of the world and every operating regime. So it's completely critical, but as I think everyone in the national security community is aware, that for decades the United States sort of had space to itself, and we could do what we wanted. It was a very peaceful domain. Today it is a very commercially valuable domain, and it's much more crowded. But also I think even more challenging for us is the fact that many other nation states now are active on orbit, and it's becoming a domain where conflict is becoming more and more a real possibility. So the question we ask ourselves at DARPA about the space domain, what we're really trying to figure out in the programs that we're doing today, the question we are asking is, what would it take to make the space domain robust for everything that we need militarily and for intelligence, and what would it take to make space a real-time operational domain, which it's not at all today. And so what does that mean in terms of programs? Well, it means you need a whole portfolio. There's not going to be sort of one magic solution to these problems. One dimension of it is launch, and I think some of the things that we're all seeing with commercial launch today are a great step in the right direction. If you think of it in terms of time to launch, how long does it take to put a new capability on orbit? We've lived for a long time where the answer to that question was years. It's going to take billions of dollars and many, many years from the time you started to really put the asset into function. I think the commercial capabilities will accelerate that maybe to months, which would be fantastic,
and just
right?
To clarify,
or even weeks.
What do you mean by it takes months? Because I think of a launch as happening in minutes.
Yeah, that moment happens very quickly, but getting ready for it, having a certified process, having all the safety and all the assurance, having the facilities and the operational capability to do that, That's a very, very long process, very slow process, and because of the demands on launch, from the day you have to put an asset on orbit to the time you can plan on a launch today is still unacceptably long. So commercial capabilities, I think, are going to help. But really, if in a time of war, we imagine if we could actually go to space not in a month or not next week, but tomorrow. Think about how that would completely change the calculus for an adversary that's thinking about taking, with an ASAT weapon, taking one of our satellites out. If we can reconstitute literally tomorrow, I think it really changes their calculus. So with that ambition in mind, we recently started, we're just now starting phase 2 actually, of a program called XS1. It's our experimental space plane. It's a reusable first stage that's designed to be able to put 3,000 or 5,000 pounds into low Earth orbit and be able to do that at a very low cost point, a few $1 million. But very significantly, the objective on the DARPA program is by the end of the program to fly that spacecraft 10 times in 10 days, something that's inconceivable with any of the spacecraft that we have today. So that, getting things on orbit very quickly, one piece of the puzzle. A second piece is what can you do once you're on orbit. We're doing some amazing work with geo-robotics and rethinking geo-architectures once you have an asset that would allow you to extend the life or do inspection or simple repairs on at geo, which is, again, something you can't do today. And then the final piece of it is all of this activity that's happening on orbit is, we do orbital catalog maintenance. We, long after the fact, we sort of forensically reconstruct what's happened on orbit, but space is becoming a real-time operational domain, and we need the eyes to see and the data to understand what's happening as it's happening, and that's another area of focus for our work.
When might we see that technology diffuse out into the public sector? Because of course there's all this excitement about Virgin Galactic and space tourism and getting goods to a space-based launch platform so we can get to the moon and then Mars. And is this potentially ever a part of that?
Yeah, the way I see it is this really wonderful and important flow of technologies. Essentially everything that happens in the space domain started with vast public investment dating back now many, many decades. Today, because of those investments, we're able now to see these commercial companies of all sorts pursuing very practical commercial markets for communication satellites, but also these really ambitious, the billionaires in space part of the story, which is really exciting, but hard to tell exactly where it'll go.
So they owe a debt to this early research.
They're able to build on it, and I think that's tremendous that they're able to take that next step. We're able to draw back from it, so when DoD certifies SpaceX for launch, that's a great example of being able to draw back from it. But then at the same time at DARPA, what we're thinking about and working towards is how do you pave the way for the next generation out beyond that. So I think that ebb and flow will continue, very important.
So let's talk about, I called it killer robots, but that's a totally unfair comparison, analogy. Really artificial intelligence, and there's this conception that we might be building, willful artificial intelligences that endanger us in some way. There are these foundations now in Silicon Valley devoted to thinking about how we're going to handle this. If anybody was going to get us in trouble with those, it seems like it'd be your organization. So
getting in trouble isn't actually our objective, although sometimes it does happen. I think it's so important that people be asking these really fundamental questions about the implications of advanced technology in general, AI in particular, and trying to think through the kinds of questions that are being posed. What I want to see is that we focus on what I think are going to be the real and sometimes much more subtle questions about AI. Just to talk a little bit about the use of lethal force with artificial intelligence. I think one of the things that we all have to be very, very clear about is that this new wave of AI, the machine learning era that we're in with artificial intelligence, it's super powerful, and we see it in our commercial lives, in our consumer lives. You go to Facebook and a picture you didn't even know someone had taken now has you automatically labeled, and it's part of trading and finance. It's just embedded in so many parts of our lives. And similarly, I think you should expect to see it more and more embedded in how we operate our military systems. But I think it's, and we're driving a lot of that in some of the things we're doing at DARPA. But at the very same time, I think it's critical that we understand what the limitations of these technologies are today. And one of the major limitations is that techniques using deep learning, this machine learning era, many times now they will be statistically able to perform better than humans. So the classic example is machines that have been trained on millions of images and now can do a phenomenal job of recognizing what's happening in the scene. Statistically better does not mean they're perfect, and the crux of the issue is that when those machines make mistakes, they make mistakes that no human being would ever make. And what that means to me is that for applications that have low consequence for each individual decision, if Facebook mislabels a photo, the world does not end, right? Mm-hmm. That's where we're going to use these technologies to great effect. On the other hand, for decisions involving the use of lethal force in my world, or decisions, critical decisions that a self-driving car needs to make, these AI technologies, this era of AI learning technologies, are not at a point where you can rely on them to make those kinds of very, very critical decisions. And that's why I think it's worth asking the question about where AI is going to go and how humanity will deal with it in the long term. But Andrew Ng, who's a famous AI researcher whom DARPA funded a decade ago and has been driving this commercially for many years, I love his quote about this. He says, worrying about Terminator today is like worrying about overpopulation on Mars. There might be a time, but it's just not yet. And in fact, I think we need to be very careful we don't let that conversation detract from the today issues about AI, like really understanding when you can and can't trust it, how it reflects. We think it's a machine and therefore it's pure in some way, but of course it's been trained on human data, and those algorithms become a way to sometimes amplify human biases. And if you don't understand that that's what that machine is giving you, I think there's some very subtle dangers that we're not really focused on sufficiently yet.
Yeah, I mean, one of the big challenges with machine learning is that it creates this black box. It hasn't been programmed, it's learned. Yeah. So I think one of your program areas is trying to shine some light inside that black box.
Exactly. It's called Explainable AI. And actually, it's a great story about our program manager, Dave Gunning, who runs that program, returned to DARPA to do that. But probably about a decade ago, when he was at DARPA in an earlier tour as a program manager, he started a project at SRI that became Siri, which became then a spin-out company called Siri that got acquired by a company named Apple, and is the historical antecedent to what we've all experienced in that commercial product, which, by the way, itself was building on top of 30 years. It was sort of the integration of 30 years of DARPA and other basic research in AI. So Dave's got a tremendous history, but with this new program, what he's trying to do is keep that phenomenal statistical power of these learning systems that give us a way to look at huge amounts of natural data, but do it in such a way that when they give us a result, we have some perspective into how they got there, as opposed to just the black boxes that we have today.
So let me get this straight. The person who started Siri is now a program manager for you, who's responsible for deciphering what these artificial intelligences are actually thinking when they give us a result.
Basically, yeah. I mean, he's the program manager. All the work gets done out in the companies and universities that we work with. But yeah, he's the mastermind behind a lot of that.
Wow. Let's talk about another program area that's I personally find really exciting, which is what you're working on. Biology is a big area for DARPA. And one really interesting part of that to me is the brain and how we enhance, manipulate, and talk to the brain. So what are some projects that you guys are working on in that area?
Yeah, this is maybe just to start by saying that biology is an area that it's been calling to DARPA for a number of years, because it's a research area in which the amount of excitement and the number of arguments at conferences and the number of papers, and the fur is flying in this area because biology is intersecting with physical science and engineering and with information technology right now. When we see all of those signs, the DARPA thought is there going to be technological surprise out of this area? And we think biology is going to be chock full of technological surprises. One dimension of that is neurotechnology. And the DARPA neurotechnology story, as with everything at DARPA, the story started with one of my crazy program managers. Jeff Ling was a doctor who had served in the Army for his entire career. He was a colonel in the Army when he came to DARPA as a program manager. He was a neurointensivist, he still is. Neurointensivist. So he was, he's the doctor. The way Jeff explains it is, if you meet me when I'm your doctor, you're lying on the bed like this and I'm looking down at you and it's not a good moment. So he was the guy that was dealing with a lot of trauma situations in theater in particular. Jeff returned from those tours in theater convinced that we needed to come up with a better prosthetic for our wounded warriors than the simple hook, which has been the standard, the standard solution for decades, for generations. And he set about to build a program called Revolutionizing Prosthetics. One part of it was to build a mechanical arm that had the degrees of freedom that our arms have, is lightweight, has all the electronics and power and everything all compactly put together. And that branch of the research has made enormous progress. I'm really thrilled that arm has actually passed FDA approval and is now being manufactured. And I think it's going to change the lives of many, many, many of our wounded veterans. Now, that device is marvelous to look at, can do amazing things compared to the hook, but it is still very, very rudimentary in the way that it is controlled. For example, you'll wear an accelerometer on your big toe, and when you twitch your toe, there's a wireless signal that tells the arm how to move. And people can master this, but Jeff, being a crazy DARPA program manager, he had an aspiration even beyond that. And his aspiration was to achieve near natural control. Why couldn't a person just think and move that arm and actually also be able to sense from sensors in the fingertips, for example, and start to really regain the kind of complete function that we all have the great privilege of with our limbs. So the second branch of his research was on understanding motor signaling and sensory signals. How does the brain translate information in and out? And that work culminated, starting a number of years ago, we've started being able to do the first clinical trials with some amazing volunteers. For example, we've had several volunteers who are paralyzed but have had brain surgery to implant these small arrays that come into contact with their motor cortex and their sensory cortex. The key here is to pick up the precise signaling. It's the very detailed signaling that you can't get from outside the brain, but that when in contact with the neurons, you can start getting that kind of precise information. And then when you can do that now, the magic is to be able to translate those signals in real time into what was your motor cortex trying to tell your arm to do. And so today we have volunteers who, with those implants, are able to think and simply move their hands in very natural ways. And critically, also to close the loop, to be able to sense the feeling of touch from sensors in those hands. And so you can imagine once you close that loop, you can start to get the kinds of, a level of function that we really couldn't have dreamed of before.
Now, just so I can visualize this, is this an artificial arm, and then there are like wires running up the back of your head to this like Keanu Reeves Matrix style plug?
Yeah, right now this is very much in a laboratory, and what you will see, the earliest experiments, Jan was a wonderful early volunteer. She had these implants on her motor and sensory cortex, had these two posts on top of her head to which electrical connections were made. And in a laboratory, that information, those signals run into a computer, which decodes in real time and then tells the mechanical arm what to do. So this is not yet, this is not a therapy. It's very much first ever lab results. But maybe just to take it one step farther, the other dimension of our research has been, can you start to get at that kind of control and sensation, not by going directly into the brain, but by using peripheral nerves, especially for amputees, where the peripheral nerves come down into the residual limb. And so very similarly now we have individuals who have chips in their peripheral, in their residual limb that connect to the peripheral nervous system, but again, the same idea that by thinking, they're able to move a prosthetic or a virtual hand, and then to receive sensation and being able to decode it both ways. So I think, awesome for restoration of function, but then back to maybe your question, as we do this work to restore function, the learning that we're getting and the understanding of signaling also allows you now to imagine what else is going to be possible. And I think the possibilities are boundless. Some of them are exhilarating, some of them are horrific, and all kinds of questions come up about control and agency and private. I mean, this really opens an incredible Pandora's box. And so I think it's an important moment and to stop and to think about what's now going to be possible and to make some very careful choices about the research paths that we want to pursue. And that's very much what we've been in the middle of.
So if you have this brain-computer interface and you've got enough bandwidth and fidelity to control a limb, that implies that you could control other things eventually.
Yep. Or even now, the woman I mentioned, Jan, we asked if she wanted to fly a flight simulator, and she did. She was a very adventuresome soul. And so she flew an F-35 flight simulator. Now, she didn't fly it gracefully or well, but the fact that she could do it at all is phenomenal. The gentleman with the peripheral nervous system chip, he's actually he's receiving sensory signal back from, he thinks and moves a virtual hand he's looking at a screen, and that virtual hand, as it touches a virtual door, he receives that sensory information back. But once you start thinking about being able to connect the brain into a virtual environment, really, you can think about all kinds of environments that you might want to pursue. So, maybe I'll tell you a little bit about maybe one of the first steps that we're taking here. One of the areas that I think is potentially of great value is to think about the potential for accelerating learning, and which is it's something we all do all the time. It's core to every advanced military function any of our sailors or soldiers or Marines ever have to do. So the question we're asking in one of our new programs is, can we develop non-invasive methods? For example, some of the research ideas involve things involving the earlobe. Are there ways to go non-invasively to send signals to the vagus nerve in our peripheral nervous system that can induce neuroplasticity in the brain?
Which is key to learning.
And when your brain is plastic is when you're able to learn. That's when the neurons can rearrange and set that information that you're trying to commit to memory. So imagine being able to learn a new language the way your 5-year-old could learn a new language because of the ability to add plasticity when you need it in that learning process. I mean, right now it seems like science fiction, but we see enough components of research that might make that possible, and so we're going to give it a try and see. So
do you have volunteers or animal trials where you're working on that now?
That we're just starting that program. If the early stages are successful, absolutely the plan is to be able to try to do those kinds of trials.
So just to put this in layman's terms, you put an electrode into, I should know this, but I forget where the vagus nerve is or how you might access it.
So that's about coming into the peripheral nervous system, which is, we wanted to choose an enhancement opportunity that did not require going into the brain, that was not invasive, that we chose neuroplasticity because we know it is something that we all, that's just a natural part of brain function that happens already. So we've tried to think about what is the first constructive step that would be sensible. It would be a huge advance if you could do it, but I think is a responsible first place to explore what's possible here.
So you could stimulate this peripheral nerve and it enhances learning.
We hope. This is the aim.
Similarly to the way, people do this with countless pharmacological solutions right now.
Right. People have tried to do this in lots of different ways, mixed results. Pharmacological solutions that our whole body and affect, they have many other implications. So this might be a cleaner way to get at it. But I think fundamentally the foundation of research, the scientific basis and understanding of what's going on sometimes has been lacking. And I mean, I think this is just something people want, and so they try doing it in so many ways. We want to see if we can build a fundamental foundation of research so that you really know what you're doing here. And if we can do that, and if it works. I mean, this is a classic DARPA program, high risk, high payoff, and we're at the beginning. But it's the kind of thing we think is worth exploring.
So given that the kind of early or middle stage scientific research that you support, as you said, it's high risk, high payoff. You never know what's going to work. You have this portfolio of bets.
Yeah.
However, DARPA's got an amazing track record, the internet, GPS. Out of all the bets that you're looking at now, and this might be the one that's furthest along, or it might just be the one that you're most excited about, what are the ones that you think are going to be the most transformative, in the next 10 to 20 years?
That's, I'm laughing because when I came into this job 4 years ago, former Defense Secretary Bill Perry said to me, who do you think was the best DARPA director in the agency's history? And I thought about it, and there really wasn't just one moment when DARPA did all the great things that it's ever done. Those advances have come out of many, many different generations. And I think it is precisely because, look, I mean, we're in the business of off-scale impact. The way you achieve that is you take risk. And we all know how you manage risk is you build a diversified portfolio, and we very consciously diversify the investment that we're making today across technology areas, military applications, time frames, in every dimension we can think of. And you build that portfolio because when you're in the risk business, you know that a lot of things are not going to fail. A bunch of other things are going to make incremental advances, which is really good. But the real point is the few things, and it won't be all of them, but a few things are really going to fundamentally change the future of national security. So ask me in 20 years, and I will tell you what I really think the answer to that is. But we've talked about some of the big bets that we're placing. I think space, a completely new architecture for space that makes it robust, resilient, and real time. That would be a revolution, and I think that's something that I think could happen with some of the bets that we're placing. But to me, that's only one example of rethinking complex military systems, and that same kind of fresh thinking. How do you re-architect the way we think about air combat or combat in the maritime domain, or controlling and seizing territory in the ground environment? All of those are places where we've had phenomenal capabilities, but we are at a point of diminishing returns with the sort of big monolithic systems that the way we've done business, very effective, is not keeping up with the world that we're in today. And so in each of those areas, you'll see a portfolio of work at DARPA where we're trying to propose completely new architectures and components for those new architectures. Some or all of those, I think, could be dramatically transformative for how we deter and defeat a very sophisticated adversary in the future. That's sort of the military systems world. We've talked about AI and some of the things that could happen there. Cybersecurity is another area where today our ambition is to be able to win at cyber. I think that's literally inconceivable in the world of cyber threats that we're living in today. Yeah. We're trying to conceive it and make the technologies for that true, and I think that might actually be technically within reach. But that's another big bet for us. And we talked about biology, so that's a sense maybe of what that portfolio of bets looks like today at DARPA.
Right, because you have at least 200 different bets.
About 200 active programs at any moment in time, right?
Right. So I would encourage all of you, if you haven't, to look at DARPA's website. You will be astonished at the diversity of bets. So I want to be respectful of other panelists' time and just say thanks for talking with us today.
Thanks, Chris. Enjoyed it very much.